Hey everybody, it's Mr. N again. Hey, that rhymes. Alright, let's take a look. We got related rates. Oh, how fun. Related rates are outstanding. You're gonna like them. Kinda.
This is 3.8 in the 6th edition and 3.9 in the 9th edition.
But let's just do it anyway. Here we go. Related rates is the idea to compute the rate of change of one quantity in terms of the rate of change of another quantity. Whoa. The rate of change of one quantity in terms of the rate of change of another quantity. So there's more than one thing changing. So usually the chain rule to differentiate both sides will be used, and we differentiate it with respect to time. Now, did I say there's more than one thing changing? Guess what? We're going to differentiate implicitly. All right, so let's talk about some strategies. Whenever we do related rates, it's always based on time. So we're going to take a derivative with respect to time. So first, read and understand the problem. Some of us just get stuck right there. Okay, but no, just kidding. But really, just read and try to decipher what the problem's asking you to do. I know sometimes you're going to read it and you're going to go, huh? Well, read it twice, read it 3 times. Underline things that are important. Try to identify variables, quantities that need to be determined. Develop your mathematical model. What do I mean by that? Come up with a formula. A lot of these will be volume type things, so you'll have to use a volume formula. Draw a picture. Often you'll have a right triangle. All right, Pythagorean theorem will be involved. Develop the mathematical model that suits the problem. Find the constants, the variables, and what was going to change over time. Some things may change. Some things may get larger. Some things may stay the same. So you need to determine what will happen there. Write your equation. Sometimes the equation involves a formula, sometimes it doesn't. But more often than not, the formula is going to be geometric or some sort of scientific application. And then here's what I was talking about. You're going to differentiate both sides implicitly. And remember what I said? It's all going to be with respect to time. So related rates, we're always going to take these with respect to time. And guess what we always use? Yep, that chain rule. It's always there. All right, so then substitute any values that depend on time and then interpret your solution. Does it make sense? Does the thing make sense? Okay, so we have this first example on a conical tank. We are not going to do this as our first example. This one is actually pretty difficult, okay? We are going to wait and do the conical tank one at the end. So I will save that for you guys, and we'll do that at the end. But let's first start with different ones. Let's look at our second example here. This second example says, an oil spill from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the radius is 60 feet? Okay, let's determine. So those of you that have science or physics or whatever, many of your teachers have you write these things given like this, right? And list all your givens, what you're told, and then you would list what you need to find. Well, if you want to go ahead and do that as an organizational way, go for it. I think that's a great method. Well, what are you given? You're given this thing. The radius increases at a constant rate of 2 feet per second. Okay, radius, feet per second. So that's going to be a change in radius over a change in time, and that's 2 feet per second. You see how I got that? That's a drdt because it's changing. The radius is changing. Change in radius per time, 2 feet per second. Okay, then it says, how fast is the area of the spill increasing? The area increasing. That tells me I need to find a dA dt. What's the rate that it's increasing, right? That's my dA dt right there. But where do I need to find this? At r equals 60. So this is another one of my given, r equals 60 feet. Okay, so let's see. What formula relates the area of a circle? Because it says circular pattern. What formula? That's going to be pi r squared. No, I know you know the joke. They're not squared, they're round. Yes, I know it's silly, but here we go. Let's do this. What we're going to do now is we're going to differentiate it. So remember I told you we developed right here in our steps. We read, we interpreted the problem, and it wants me to find out how quick, how fast the area is changing based on how fast that radius is changing. I know how fast the radius is changing, so how quick is it affecting the area? So I have this circular oil spill like this. This radius is 60 feet, right? And I know that this radius is changing at some sort of rate of 2 feet per second. Okay, so I need to find out how is it impacting this area? How quick is the area changing based on the radius changing at that rate? All right, so let's take a look here. Since I have a dA, I followed my steps, and now I wrote my equation. I did step 1, step 2, step 3. I understood the problem. I interpreted a mathematical model. I wrote an equation, dA equals pi r squared, and now I need to differentiate. So here's what I'm going to do. I'm going to differentiate both sides, so dA dt with respect to time. And this, I took the derivative of the left side, and now I'm going to take the derivative of the right side. Remember, pi is a constant, 3.14. So I end up with 2 pi r dr dt, right? Implicit differentiation. Remember when we were doing implicit differentiation, I always said dx over dx, cross it out, because I was taking the derivative of x with respect to x. Now everything that I'm doing is going to be with respect to time, so I need to keep all those variables. If I have a dA, it's going to be over dt, because it's always going to be with respect to time, so it'll stay in there as part of my equation. Okay, so now, what do I know? Well, I know that I need to solve for dA dt. I know 2, I know pi, I know r, oh, they told me when it's 60 feet, and I know dr dt. They gave me dr dt as 2 feet per second. So now I can finish solving this problem, and I multiply all this out, and I get 60 times 2, 60 times 2 is 120, times the other 2 is 240, so 240 pi feet squared per second. That's how quick that area is changing. If you want to express this as a decimal, it's approximately 754 feet squared per second. Okay, if you multiply it by 3.14. All right, let's take a look at the second one now. On the second one, again, let's list what we are given after we read the problem. It says, air is being pumped into a spherical balloon at a rate of that. Wait, look at this. Cubed. That's a dV/dt. Find the rate of change of the radius when the radius is 2 feet. Okay, so I have a spherical balloon. Here are all the things I'm given. I am given some sort of spherical balloon. And there's my sphere. You tell me if I did a good job with it. And I'm pumping air into it. And what's the rate? That's what's changing, is the dV/dt at 4.5 cubic feet per minute, right? It's a dV/dt because it's a cubic foot per minute. What I need to find is, as I'm doing this, what is the radius? Find the rate of change of the radius. What is this rate of change of the radius? That's what I'm looking for. That's how I express dr dt is the rate of change of the radius with respect to time, and that's what this problem wants me to find. But I also know something else. They tell me when r is 2 feet. Well, what formula do I use for a sphere? I have a volume formula, and that's 4/3 pi r cubed. All right, so let's take a look at this and see what we could do with all this. I wrote everything down, I developed a formula, I understand what's happening. What's happening is the volume is changing, and as the volume changes, how is the radius changing? That's what I need to find. And so I know all that stuff. Next step in my process is to take a differential, and I will differentiate both sides. So I'll get dv dt on the left side. On the right side, I'll get 4 pi r squared dr dt, right? Because I took the derivative of r with respect to time. All right, what values do I know? I know dv dt. Plug that in. 4.5 equals 4 pi. I know r. That's 2. I'm solving for dr dt. That's what you're looking for. Okay, so now how do I solve it? Well, I'm going to divide everything over to the other side. So I end up with dr dt as being 4.5 divided by 8 pi, and we'll put that answer over here. Dr dt comes out to be 0.0895 feet per minute. There you go. Easy enough so far? I don't know. You tell me. Related rates can be tricky, but you know what? Once you get these, once you get the process, once you start doing more of them, you get them. They start sinking in. That's the beauty of related rates. With at least most of them. Sometimes some of the authors in the books can get really funky with the problems, but the good news is they won't give you something that crazy on the AP test. Okay, so let's take a look at this next one. It says an airplane is flying on a flight path that will take it directly over a radar tracking station. See the diagram. If S is decreasing at a rate of, 400 miles per hour, when S is 10 miles, what is the speed of the plane? Whew. Okay, let's look at this. If S, here's what S is right here, this is my S, and this is decreasing, and I have a rate that this is decreasing. So in other words, the plane is going this way, and this S is getting smaller. When S is 10, what is the speed of the plane? The speed is going to be on the x-axis, a horizontal speed is what I'm looking for. Okay, so that's what it's asking me to do. So let's list out what we have given. All right, so we are given right here this plane, and we're given that the speed ds dt with respect to time is decreasing negative 400 miles per hour. We have s as equaling 10 is when we have to solve it. We know that this is 6, this is not changing, and we have to find the horizontal change, that horizontal speed, which is the dx dt is what I am looking for. All right, let's take a look at something here. When this is 6 and s is 10, when that's 6 and s is 10, I can solve for x, right? Because I have this right triangle with this being 6, that being 10. This will be 8. It's a Pythagorean triple. So you really don't have to do much. You get it. It's going to be 8. So I solve for x. So that means when s is 10, x will be 8. That's another little tidbit I can put in my given. Okay, what formula am I going to use here? Okay, now I got to try to develop a formula. Oh, I see a right triangle. I know that a squared plus b squared equals c squared. Well, in the case that I'm given, I know that x squared plus my constant 6 squared is going to be s squared. Okay, x squared plus the constant 6. I didn't put a y there because I knew it was going to be a constant. I'll show you how to do it with a y in a minute. Okay, let's take the derivative here. I'm going to implicitly differentiate now that I've developed the formula. Now I know what I'm solving for. I'm going to implicitly differentiate. So this gives me 2x dx dt plus 0. The derivative of a constant is 0 equals ds. Oops, sorry. I need to put 2s and ds dt. So that's what I end up with there. Now suppose you left the y in there. Suppose you called this y. You would have x squared plus y squared equals s squared, 2x dx dt plus 2y dy dt equals 2s ds dt. I'm showing you this because there are going to be times when the y does change as well. But look, in this case, This is a constant 6 miles overhead. So is my rate in the y direction changing? No, it's always going to stay 6 miles overhead. So this rate right here is 0 anyway. So that's why we just kept it as a constant, because it's not changing. Okay, so now over here, let's take a look. Do I have an x value? Sure, I do. It's 8. Do I have a dx dt? Nope, that's what I'm solving for. Okay, equals 2. Do I have an s value? Yep, that's 10. Do I have a ds dt? Yep, that's negative 400. Okay, now I can solve all this. So solving this yields dx dt as being negative 500 miles per hour. Okay, why is it negative 500 miles per hour? Because I'm moving this way. I'm moving to the left, you see? So the numbers came out. The numbers worked out because I'm moving to the left. So now let's take a look at what we have next. Oops. All right, so this number 5 is the famous ladder problem that we see. And it says a ladder is 25 feet long and leaning against a vertical wall. The bottom of the ladder is pulled horizontally away from the wall at 3 feet per second. How fast is the top of the ladder sliding down from the bottom of the wall? Okay, let's draw what's happening real quick. Before I do this problem, let's draw. We have a ladder leaning up against the wall. So here is my wall. Come on. Here's my wall. And I've got some sort of ladder leaning up against it, like this. And they tell me that this ladder is 25 feet long. And then here's my ground right here. We'll put the ground level. Let's just do this color for now. We've got this ground level right there. Here's my ladder. My ladder is 25 feet long. The bottom of the ladder is pulled horizontally away from the wall. So this ladder is being pulled in that direction, right? This is an x direction. I can call it in the x at 3 feet per second. So this is all my givens right here. It's being pulled away. That's a dx dt of 3 feet per second, right? It's the rate, so that's why it's a dx dt. It's moving away from the wall at 3 feet per second. How fast is the top of the ladder sliding down? Oh, okay. Top ladder sliding down. dy dt. So in other words, this point is coming down this way, right, along the wall. That's going to give me the dy dt value that I'm looking for. So I need to find dy dt when the bottom is 15 feet away. So now I know that that's 15. Okay, that's a right angle, kids. You all know that. So what formula am I going to use? I'm going to use the Pythagorean theorem again. X squared plus y squared equals c squared. Well, I know the ladder is 25. This is my c. Is the ladder changing length? No. C is a constant in this case. Okay, so this is the only constant term in this situation because the length of the ladder is not changing. The x is changing, the y is changing, and I have a dx and I have a dy. All right, so now let's do the next step in our process, and we are going to differentiate this. So let's take a look at what we got. 2x dx dt plus 2y dy dt equals 0. Why is it 0? Because that's the derivative of a constant. All right, is there something I need? Yep. I know that this is 15. I know that this is 25. I still need that y value. So y is going to be the square root of 25 squared minus 15 squared. And that comes out to be 20. All right, so now let's plug all our values in. 2 times x, well, we know x is 15 plus, oops, I need the dx dt. I forgot to put the dx dt. I know that that's 3. So let's put that in times 3, right? That's my dx dt, plus 2y, which was 20, and dy dt, which is what I'm solving for, equals 0. All right, so 40 dy dt equals, this becomes 30 times 3, bring it over, negative 90, dy dt is going to be negative 9/4, which is negative 2.25. I'm going to ask you again, this is feet per second. I'm going to ask you again, why is that negative? Why is that negative? Because it's moving down. All right, it's moving down. Next problem. We are moving right along here. Okay, now we've got a camera mounted at a point 3,000 feet from the base of a rocket launching pad. Ooh. If the rocket is rising vertically at 880 feet per second, okay, vertically, dy dt, rising, feet per second, dy dt. When it is 4,000 feet above the launching pad, there's my y, okay? How fast must the camera elevation angle change at that instant to keep the camera aimed at the rocket? Oh, wait, that changes things. Do I have an x? Okay, well, let's just draw it out and see what's going on. Besides, you know you like my famous drawings. Okay, so let's go ahead and do this, and we have some sort of rocket and a camera right here. We'll call this the camera, is mounted at a point 3,000 feet. This is 3,000 feet from the base of a rocket launching pad. Here is my pad. This is the base of the rocket launching pad. If the rocket, ooh, cool, I get to draw a rocket. Woohoo! There's my rocket. And you got this. I guess we could put, like, let's do this. Let's have some fun with this. We're going to put USA right there. And the flames coming out. Look at that. I wonder if this is SpaceX. Right? It could be a SpaceX rocket. Anyway, so it's going up, and it is rising vertically at 880 feet per second. So I'll just call this y, instead of y, let's just use h, okay, because the height. So this h, here's all that I'm given, this drawing with all the things I'm doing here. This dh dt is 880 feet per second, and I know that the height right here, h, is 4,000 feet. Okay, I drew everything. What the heck am I solving for? How fast must the camera elevation angle change? There's theta. That means I need to find d theta dt. Oh, so this camera changes this angle to stay aimed at the rocket to keep the rocket in sight. I need to know what that angle is changing at. Oh, how the heck can I relate these? Well, let's take a look. I got the triangle. I got a height right here, and a dh dt. I got an x right here. The x is not changing. There is no dx dt, but this angle is changing for a d theta dt. And check this out. What relates right here? The opposite and the adjacent. The tangent. So the tangent of theta equals h over x. But guess what? X is a constant, so I could go ahead and plug it in. So let's do that as we break this problem down. I know the tangent of theta will be h over 3,000 because this is a constant. It's not changing. All right, so that means I can take the derivative. I have my formula, I develop my givens, I know what I need to find, I've made a picture, I have the equation that I need. Let's implicitly differentiate. So over here, the derivative of tangent is secant squared theta d theta dt. Over here, okay, this is like saying 1 over 3,000 times h, because that's my constant. Remember, x is not changing, it's a constant, so I could just express it in this case just by putting 1 over 3,000. So this becomes 1 over 3,000 times, the derivative here is 1 dh dt. All right, I know a bunch of values. I know my angle. Wait, I don't. I don't know what theta is. Oh, but I can get it, right? Because I know that this right here is theta, this is 3,000, and that's 4,000, right? So I know that I can solve for theta if I need to. Or you can go with the flow and you can say, all right, it's a right triangle, that's 5,000. At this point, you can solve for theta, okay? If you really want to solve for what theta is, you can. But I'm just kind of doing it a puristic approach, kind of like the mathematical purists like. So I'm putting 5,000 there, and so then I could say, all right, I can find what the secant of theta is just on its own. What is the secant? The secant is 1 over the cosine of theta. And what's the cosine of theta in this case? The cosine is going to be 3,000 over 5,000. 3,000 over 5,000. So really, the secant of theta is just 5/3. Right? Take that, find that. I'm just doing a little trick. You could have found the angle, plugged the angle in, and worked with it that way. You'll get the same answer in the end. Okay, so you could actually find what theta is, use the tangent. Tangent theta is 4,000 over 3,000. Solve for theta, plug it in right here. But I kind of found what the whole secant is, 5/3. Because now I can just put that in here. So I'm going to say 5/3 squared, right? D theta dt equals 1 over 3,000. Well, what's my dh dt? They told me that's 880. Okay, at this point, I can solve for d theta dt, and that's going to give me 0.1056 radians per second. And if you want to change this to degrees, that's 6.05 degrees per second. All right, so there you go. There you go. All right, so let's take a look at this cone example. And it says, water runs into a conical tank at a rate of 9 cubic feet per minute. Cubic feet. Right away, I know that's a dVdt. Okay, the tank, that should say tank. Let's fix that, not the take. The tank stands point down with a height of 10 feet. Okay, so I know a height and a base radius of 5. I know a radius. How fast is the water level rising when the water is 6 feet deep? Okay, let's draw what's going on first of all. Let's try to decipher what we have to do. Let's draw the inverted tank. So it says it's a conical tank, so it looks like this. These are all my givens. Let's list them again. And I have this water tank like this. And water runs in at a rate of 9 cubic feet per minute. So that's a dVdt because it's change in volume, cubic, right? Cubic feet per minute. dVdt is going to be 9 feet cubed per minute. And then we pointed the tank down. The height of the tank is 10. So this total height of the tank is 10. And the base radius, which is that radius is 5. Okay, so the radius equals 5. These are all my givens so far. All right, so here's what I need to find out. It says, how fast is the water level rising? So that means there's water in here, and it's rising at some sort of level right in here. So it's not full. It's rising.
and that means it's going up, so that's a dH dt that I need to solve for. Okay, so I have to find that dH dt, but look at the condition. When h is 6, okay, when the water is 6 feet deep. Whew. All right, what else do I know? I know the formula for the volume of a cone. The formula for the volume of a cone is 1/3 pi r squared h. Okay, so these are all the things I know, and I have what I need to find. All right, let's see what we could do here. All right, so I've always said when you do this, you have to implicitly differentiate. Okay, but there's a catch here. I got two variables that are changing. Let me explain that to you. I have r. As the height changes, look at the radius changes too. So at 6 feet right here, there is a completely, we'll say that's 6 feet, there is a completely different radius than when I'm at 10 feet right up there. Okay, so as the height changes, the radius changes. So if I want to work this out, these two are not constants. So I would need to implicitly differentiate, and I would need to find a dr dt and a dH dt, but I'm not given anything here about a dr dt. Okay, so what do I do in this case? Oh man, this is giving me a headache. I get confused here. What do we do? What do we do? Okay, well, we have to try to find a way around it, and I'm going to give you a hint. Cones have a ratio, and we can substitute something in the ratio, because look, here's what I'm saying. This is linear, right? These two are both linear. So as the height changes, the radius changes proportionally. And so what I can do, it's a little trick to do with cones. I can just set it up and use only the variable I need to know. So let's do that. Okay, and here's what I'm saying. Let's set it up so that we use only the variable that we need. Okay, so I've got this height right here like this. This is 10, this is 6. Oh, sorry, 5. And I want to know when this is h, some sort of height here, what this r is. So do you see how this will be a proportional, it's a similar triangle. You have one triangle in here. Going back to geometry, oh boy, we've got similar triangles. Let me break the triangles apart for you. You've got this one, that's 10 by 5, and then you've got the little one in here that's some sort of h by r. So you can set up a ratio. We could say 5 to 10 equals r to h. So what are we going to do with this ratio? Well, look, I need to solve for dH dt. So I just want to keep this in terms of h. If I want a dr dt, then I would change it to say, okay, I want that to be in terms of r. But because I want dH dt, I'm going to keep that in terms of h. So what does that mean? That means I need to substitute an r, so let's solve for r. So I can cross multiply, and I get 5h over 10 equals r. So 1/2, or we'll just say h over 2 equals r. Okay, now I'm going to put this into there. It's important that you do that and make that substitution before you differentiate, because if you differentiate before making the substitution, then you have to use the product rule, then you have to make sure you differentiate with respect to r and h, and then you'll have that dr dh, which you can't do anything with. Okay, so again, we solved for r, and why were we able to do that? Because we had a ratio, because this is linear and it's a special situation on cones, that this ratio will remain constant throughout, so I can make that substitution right in here and get rid of the variable that I don't want. So let's finish this out. So let's go ahead and write this as v equals 1/3 pi, and then r is this h over 2 that we said, squared times h. So this gives me 1/3 pi h cubed over 4. So I did this squared, h squared over 4 times the h. So I got h cubed over 4. So let's go ahead and clean this up a little bit. So the volume is going to be pi over 12 times h cubed. The way I wrote it is so that I could put the constant out in front, and now I can differentiate. So dv dt, left side. Now on the right side, I get pi over 12, which is the constant, and this is times 3h squared dh dt. All right, let's see what I got. I have all the info I need. I have dv dt as being 9, right there they told me. Pi over 12 times 3. I have the h. I need to know when h is 6. When h is 6 is when I'm solving this for. So 6 squared times, and this is what I'm looking to do, find the dh dt. So this becomes 9 equals, and this will end up being 36, and this will reduce there to be a 4, so 36 over 4 gives me 9 dh dt, and there's a pi, sorry, dh dt, so these reduce out, so 1 over pi equals dh dt. So basically I just solved it for dh dt right there, and 1 over pi comes out to be approximately 0.32 feet per minute, and that's my dh dt. You can leave it as 1 over pi, that's fine. All right, so the tank inverted cone ones are a little bit difficult, but the key to it and what you need to remember is right there. Can you convert this ratio to solve for what you need? All right, I've got many more videos on different types of related rates that you'll see, so check those out. I think I've put them in a playlist for related rates, so hopefully that will help you out. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.